The creation of a 92% human-identical android begins with pure molecular materials, refined inside high-precision chemical facilities. Medical-grade platinum silicone provides the foundational base for synthetic skin, engineered to match the elasticity and thermal conductivity of biological tissue. Alongside synthetic polymers, solid aerospace titanium ingots arrive for structural frame processing, chosen for extreme strength and minimal weight. Automated transfer systems transport these critical raw materials directly into processing bays, maintaining strict environmental purity from the moment of arrival. Laser spectrometry verifies metal purity down to parts per million, ensuring every structural component can handle thousands of hours of continuous movement. Before machining begins, the metal undergoes multi-stage stim cleaning, eliminating foreign microscopic contaminants that could compromise joint tolerance. In the machining bay, computer-guided multi-axis mills carve the anatomical skull frame with sub-micron precision, sculpting internal cavities for micromotors. Simultaneously, liquid silicone enters vacuum degassing chambers, where negative pressure extracts microscopic air bubbles, preventing surface defects in the skin. The degassed silicone is injected into high-detailed anatomical molds, where controlled thermal pressure cures the material into soft, durable epidermal sheets. Precision automated airbrushes then deposit micro-layered pigments, simulating complex subsurface light scattering found in living human skin. Waterjet cutters precision trim the cured silicone plates, fashioning tiny passages for micro-wires without warping the delicate synthetic skin. Inside the skull frame, specialized robotic arms seat dozens of micro-servos, providing the precise articulation needed for human-like facial expressions. Flexible neural wiring is threaded through the titanium vertebrae, shielding power lines against electromagnetic interference during rapid head movements. Synthetic muscle fibers are calibrated for tension, mirroring the force displacement profile of human jaw muscles to enable subtle mouth movements. The transition to true realism requires human artistry. Skilled technicians manually route hair strands into the silicone matrix, one by one. Eyebrows and lashes are crafted with extreme care, ensuring the symmetry and density exactly reflect natural biological features. Once detailed, the completed skin mask is fitted over the robotic frame, aligning magnetic mounts with the internal servo network. Initial power tests trigger automated expression calibration, synchronizing micro-servos to replicate subtle human facial expressions. Internal thermal management systems are monitored, verifying that embedded heat elements distribute warmth evenly across the facial surface. 3D optical scanners perform a final structural sweep, matching the facial topography against biological reference models. Following functional validation, the structural chassis undergoes automated surface polishing, eliminating micro-abrasions along all visible metal joins. A fiber laser permanently marks each unit with its unique production sequence and authentication signature at the base of the central neck column. Technicians perform a manual detail cleaning, clearing residual particles from micropores and ensuring flawless visual presentation. The android is outfitted in custom apparel designed to accommodate joint articulation while maintaining a natural human profile. System protocols initiate standby mode, powering down non-essential sub-processors before the unit is prepped for transport. Automated hoists transfer the unit into specialized flight cases lined with custom-molded shock-absorbing foam. Safety restraints lock the chassis rigid within the transport enclosure, protecting sensitive micro-actuators against vibration during transit. The flight case is sealed, and environmental controls maintain stable temperature and humidity levels throughout international shipping. From the clean rooms of next-gen bot labs, completed units are loaded onto climate-controlled transports bound for distribution worldwide. Combining advanced materials with precision engineering, the result is a synthetic humanoid that bridges the gap between technology and humanity. Subsurface motion dampeners absorb micro-vibrations, ensuring every subtle facial twitch moves with fluid human authenticity. Durometer testing confirms the epidermal elasticity matches human palm softness, maintaining grip friction without tearing. Integrated microfluidic heat loops circulate temperature-controlled fluid, replicating normal human resting body heat across every extremity. Multi-joint dexterity algorithms run high-speed articulation checks, verifying that synthetic fingers can manipulate delicate objects effortlessly. Stereoscopic optical sensors are aligned to sub-millimeter tolerances behind the synthetic irises, granting the unit natural spatial perception. Acoustic profiling inside specialized chambers guarantees that internal cooling systems operate below 15 decibels, ensuring whisper-quiet operation. High-speed gyroscopic sensors process posture feedback thousands of times per second, executing instantaneous balance micro-adjustments. Optical motion capture maps, spine curvature, and skin deformation, refining software controls to eliminate artificial, rigid movement patterns. Final cosmetic conditioning coats the silicone surface with protective anti-glare agents, perfecting its human appearance under any lighting condition. With every subsystem calibrated and verified, the android achieves a 92% human realism score, setting a new benchmark for robotics. Continuous stress testing verifies that joint actuators maintain zero backlash precision, even after millions of repetitive structural flex cycles. Torque mapping sensors track real-time structural load across the shoulder girdle, preventing internal stress fractures during heavy lifting. Sub-zero climate chambers evaluate thermal regulation, confirming that synthetic skin maintains flexibility and warmth in extreme Arctic environments. Infrared heat arrays test high-temperature endurance, ensuring internal liquid cooling channels successfully dissipate excess thermal buildup. At the core of the android lies an advanced neural processor, translating sensor data into natural motor responses in fractions of a millisecond. Final firmware uploads, flashing core behavioral algorithms and speech synthesis models prepare the android for autonomous human interaction. Tactile sensor arrays embedded beneath the artificial fingertips undergo sensitivity tuning, allowing the unit to detect microscopic surface textures. Closed-loop pressure feedback loops regulate grip strength instantly, granting the android the delicate dexterity required for complex hand tasks. Integrated movement systems synthesize balance, fluid stride length, and posture control into a seamless, lifelike walking gait. Micropneumatic chest actuators replicate idle breathing patterns, completing the visual illusion of living biological presence. Quality assurance protocols wrap up with fine optical sign-offs, verifying pupil response metrics under varying illumination levels. Protective face guards seal delicate facial structures during shipping, safeguarding microsensors from particulate contamination. Tamper-evident holographic security seals are applied to the transport enclosure, guaranteeing factory calibration integrity upon delivery. Transport units embark on worldwide dispatch, carrying cutting-edge humanoid robotics to research facilities and private clients. From raw titanium and liquid silicone to 92% human realism, next-gen bot labs redefines the future of autonomous synthetic life. Next-gen bot labs. Engineering tomorrow, today.